to join. Yeah, thanks, Vina, for recording the video. So today we are very happy to have Ben from University of Oxford talking about completeness for fault equivalence of Clifford ZX diagrams. So this will be around 1 hour plus including both the seminar and the Q&A. So Ben, do you want to have the question in the middle, or do you prefer to have all the questions at the end of the topic, at the end of the talk?
No, feel free to interrupt me if you
Okay,
have
cool.
questions.
Cool, great. If
Yeah,
there are
might
any
not.
questions from audience, feel free to put it in the chat or just open your mic and yeah. Right.
Yeah,
Yeah, thank you very much. And please take the stage.
awesome. Are you going to monitor the chat because I might not
Yeah,
have
yeah,
a
I'll monitor the chat. Yeah, no
perfect.
problem.
Thanks.
Yeah.
That's amazing. Awesome. Yeah, cool. Hi everyone. Thanks a lot for having us. Um, I'm here to talk about actually kind of two papers of ours. The first one is fault-tolerance by construction with Baldy Zapur and Alex Kissinger. And in it, we introduced this idea that in fault-tolerant quantum computing, we don't only care about like the linear map that our circuit implements, but also the behavior of our circuit under noise. And we define this notion of fault equivalence. So when two circuits can be considered to behave the same under noise, and make the case that you can use this to construct fault-tolerant gadgets that are correct by construction. Um, and this notion of fault equivalence is something that's at this point quite close to my heart. A lot of my research these days is built around fault equivalence. And one of the questions that we then ask after having introduced this idea of fault equivalence is kind of, do we actually have a complete calculus for fault equivalence, which I'll introduce a little bit further later on what exactly that means. So this talk is basically split into two parts. First, I want to kind of introduce and motivate the idea of fault equivalence and how it can be used. Once you are hopefully semi-convinced that this is worth thinking about, I'll then get to the second part where we talk about the completeness and then the slightly more algorithmic side of things. So yeah, let's start with fault tolerance by construction. And I'll start with the ZX calculus. So maybe kind of to point this out, in our paper we originally defined everything on circuits, and maybe in the formalism you guys might be slightly more familiar with. But since especially also the second paper is now working in the ZX calculus, I'll just do everything immediately in the ZX calculus and hopefully kind of try to motivate how this actually corresponds to quantum circuits and everything. So the ZX calculus is a tool actually developed here in Oxford about quite a while ago at this point, 15 years or something. And it's a diagrammatic way for representing quantum circuits. It consists of these two generators, the green Z spider, defined in the Z basis, and the red X spider, defined in the X basis. And we can basically read this as a tensor network with very specific generators, namely exactly those two generators. And we can compose them. We can either compose them sequentially, corresponding just to matrix multiplication, or we can compose them in parallel, corresponding to the tensor product. And it turns out that these two generators are actually sufficient to represent any linear map from n qubits to m qubits. So a lot of the circuit components that we know and care about can very naturally be expressed in terms of ZX diagrams. I quickly want to point out that this is the Clifford fragment of the ZX calculus, which represents stabilizer circuits, which is kind of what we will be thinking about here in this talk and in error correction, at least this part of error correction. So we can represent gates in terms of these Clifford ZX diagrams. But there also exists other fragments of the ZX calculus that are universal for arbitrary linear maps from n qubits to m qubits. So we have state preparations over here, we have single qubit unitaries, we have multi-qubit unitaries, and then we also have measurements where the parameter of these spiders here, the k, either being 0 or 1, indicates the measurement outcome. And in a way, you can think about these spiders as breaking circuit gadgets into their constituent components in a way. But the real power in my mind of the ZX calculus is not in its ability to very naturally represent quantum circuits, but more importantly, to reason about quantum circuits, because it comes with a rewrite system that that allows us to manipulate these diagrams while preserving the linear map that they represent. So we can actually change the diagram and the way it looks, but we preserve what it means. And we have these rules here, and then a very important meta rule, only connectivity matters, which is the basic idea that it doesn't matter where we put our spiders in space. We can move them around wildly as long as the connections between the spiders remains unchanged. The underlying linear map that these diagrams represent also stays the same. And this is actually a surprisingly powerful rule that, as simple as it is, allows us to do quite a bit. And we can use the ZX calculus and these rewrites to synthesize and optimize quantum circuits. A very simple example might be the cat state. So we want to prepare a four-legged cat state. The way we can synthesize a circuit that does this using the ZX calculus is we express the cat state as a ZX diagram, which is simply a single spider with four legs. And then we can use our rewrites to manipulate that diagram until eventually we get a new one that actually looks like a quantum circuit. So we have our state preparations here, we have a sequence of CNOTs, and we can now simply extract the corresponding quantum circuit. And by the way that we constructed this circuit, we are guaranteed that this actually implements the cat state, because we are guaranteed at each step of our rewrite, we preserve the underlying semantics, the linear map that our diagram represents. And therefore, we are guaranteed that whatever circuit we get out in the end does implement the cat state. And this is kind of already a spoiler for how we will be doing fault tolerance by construction later, where we don't only have to care about the linear map, but also the behavior of our circuit under noise. And to do this, we first have to introduce the notion of noise on ZX diagrams. In line with the space-time papers, Delfosse and Bacon and Gottesman kind of will be considering Pauli faults in Clifford circuits. So we have our Clifford circuit. We consider the fault locations, the places where things can go wrong, to be the time steps in between our gates. So these are the places where Pauli actions can occur. And a fault in space-time is simply a Pauli that affects some of these edges with either X, Y, or Z rotations. Mathematically speaking, we can just model faults on a circuit as elements in the Pauli group to the number of fault locations, where kind of the empty ones simply are identity rotations or identities, and then each other element kind of indicates how the Pauli would act on that circuit at the specific location. And then when we have a circuit and a fault, we will write C to indicate the circuit, and then C to the F to indicate the faulty circuit if fault F in particular has occurred. So this is the circuit we would get if we just replaced every fault location by the according rotation. And then for ZX diagrams, we can define exactly the same thing. Here now we will say that the fault locations are simply the edges in our diagram, and a fault on a ZX diagram is an element in the Pauli group to the number of edges. And once we defined the notion of faults, one question is, okay, what is the noise model that you're assuming? Are you assuming phenomenological noise, circuit level noise? So what's the noise model that we kind of want to think about? And first of all, we'll just give a general notion of a noise model. The way we think about this is we have these atomic faults. These are the individual fault events that can occur. We can have a qubit flip, a measurement fault, we can have a gate fault. This corresponds to the independent error mechanisms that you might know from STIM. So if we have some sort of set of atomic faults that we choose, depending on what we want to prioritize and think about, then the set of all possible faults under that noise model is simply the group generated by our atomic faults. And then to give a way to indicate the likelihood of a fault, we'll assign each atomic fault a weight, where higher weight faults are less likely. So we might say that, let's say, measurement flips have a weight 1 and idle errors have a weight 2, for example, if we wanted to kind of give those different values. And then for kind of higher, like generated faults that consist of many atomic faults, we simply take the sum of the atomic faults, of the weights of the atomic faults to calculate the weight of a larger fault. Um, Now, as I said, there are different noise models that kind of all fall into this category of weighted noise models. We can kind of define a circuit level noise model, a phenomenological noise model. But one noise model that is particularly easy to work with and that we'll use throughout the rest of this talk is what we call edge flip noise models. And edge flip noise models are simply noise models where each atomic fault affects at most one edge. This might seem very simplistic, and it is, but I'll later argue why this is actually kind of sufficiently expressive anyways, as long as you're being careful. And more generally, I do want to point out that these nuances between different noise models in ZX and circuits is something that we can take care of in fault tolerance by construction and so on. But for the sakes of time, I'll be a little bit more quick about that for the purposes of this talk. But if you have any questions, feel free to kind of ask and I can elaborate. One big advantage of edge flip noise models is that we can depict both the diagram and the noise model in one figure, where we simply kind of write the weights of each particular edge flip on each edge. So we can have X, Y, or Z edge flips. So we get X, Y, or Z values. And then when our noise model does not kind of include a certain edge flip, we simply indicate that with a bar. And then for the purposes of notation, what we'll do is we have certain edges that might not allow any edge flips. We'll indicate those as purple edges. This is obviously not something we can do in practice. This is not something we can require our quantum computer to do, right? We cannot, what we call these idealized fault-free edges. We can't tell our computer not to do faults here, but they are very useful mathematical notions to kind of think about what we would like to have and maybe to mathematically reason about the relationship between different diagrams. And then the other kind of shorthand that we'll be using is that oftentimes we primarily care about Z faults for like technical reasons and remove X or do not allow X or Y faults. So whenever we have an edge where we only allow Z faults, we'll indicate the weight of that edge as a single number, which just means that X and Y faults are not allowed on that particular edge under this particular noise model. Okay, and now that we've defined the idea of noise models, one last question that we kind of should talk about briefly is this idea of like, so when is a fault detectable? There are different ways of thinking about this. I think kind of the most intuitive notion is we have these detecting sets, so kind of sets of measurement outcomes whose parity in the noise-free case is predetermined, and a fault is detectable if it flips odd many measurements of some detecting set. For a range of mathematical reasons that happen to work out quite nicely, it turns out that we can equivalently state a fault is detectable if the faulty diagram that we get, right? The d to the f was the diagram that we get if f occurs. If this faulty diagram actually is zero. I think the exact precise details here are not important. An intuition could be we can consider d to be post-selected on an expected measurement outcome. And if d to the f makes that diagram go to zero, then the probability of us seeing that expected measurement outcome is zero. Or in other words, with 100% probability, we'll see an unexpected measurement outcome and therefore get a non-trivial syndrome and therefore know that something must have happened. So that's maybe a little bit of an intuition behind why this is our definition of detectability.
Just quick, make sure I understand as I'm new to ZX still. So if I go to zero, do you mean that in the ZX rules, it like eliminates the graph down to something simple? Like what does go to zero mean in this case?
Yeah, so I mean, in terms of like, there's two ways of thinking about it, but I'd say so the linear map that the ZX diagram represents is all zero, is the zero linear map.
Okay.
And that does also mean that the graph will trivialize in some sense, but like essentially the linear map is just the zero linear map. Yeah.
One more question about this.
Mhm.
So I thought that these diagrams represented unitaries. So is that correct, or could it be?
They can also include preparations and post selections. So
Oh,
they
I
are
see.
actually any linear map from n qubits to m qubits. Yeah.
I see. Okay. Yes,
Yeah.
thanks.
Okay, so fault equivalence. Now, one thing we care about is what is actually the linear map that our circuit implements, but another thing we care about is how does my circuit behave under noise? And the fundamental observation behind fault equivalence is that two circuits, even though they implement the same linear map, might not behave the same under noise, and that a fault on one circuit might be much more detrimental than a fault on another circuit. As an example, let's consider these two circuits. On the right-hand side, we have a quantum circuit that prepares the cat state. This is kind of the quantum circuit, but as a ZX diagram. And then on the left-hand side, we have a magic box that fault-freely, without anything going wrong, it's idealized, right? It's in purple here, that fault-freely prepares the cat state. And the only things that can go wrong are actually edge flips at the very end of my circuit. Let's compare these two circuits. Clearly, one of them has already way more fault locations than the other one. But in particular, what we are worried about here is that there exists faults on our right-hand side, single faults that propagate out to create multiple faults on our data. So if I have a single edge, if I have a single X-type error on the control of the CNOT, this actually creates two errors on my data. This is problematic. If I have a circuit with distance 2, meaning all faults of weight 1 are detectable, where I have a circuit that includes this magic box, and now I replace this magic box with a potential implementation, then all of a sudden there exists a single fault that propagates out to become a fault of weight 2, and might therefore, in my overall circuit that you previously had distance 2, be undetectable. So if I replace this idealized circuit with this particular implementation, I may have reduced the distance of my overall circuit. So to formally capture what goes wrong here, we introduce this notion of fault equivalence. Two circuits, C1 and C2, under their respective noise models F1 and F2, are considered fault equivalent if for all faults F1 on C1, we have either F1 is detectable, in which case we don't really care about the fault, we can take care of it later in the decoding, or there exists a fault F2 on C2 that first of all has the same effect. So the kind of faulty map I get on C1 under F1 is the same as the faulty map I would get on C2 under F2. But importantly, F2 should have at most the same weight as F1. And to make this an equivalence relationship, we also require the same for all faults F2 on C2. Now, the place where this goes wrong in our counterexample is that, oh yeah, that should be X's here, but that there does indeed exist a fault on the left-hand side that has the same effect as the fault on the right-hand side. So we can find an F2 such that the faulty linear maps are the same. However, on the left-hand side, two things have to go wrong to have the same effect as this one thing going wrong on the right. And this, in my mind, means these two circuits are not the same. There is a fault on one circuit that propagates worse than any single qubit flip on the other circuit. And this idea that for every kind of undetectable fault over here, there should exist a corresponding fault over here and vice versa, this is fault equivalence. This is kind of one of the key notions that has been underlying a fair bit of our work lately. And I'll try to convince you that this is a useful notion by recovering some things in the literature. So I'll try to make the case that a lot of people that are thinking about circuits under noise, I either kind of implicitly already care about this notion. And the way I'm going to do this is by recovering known definitions in terms of fault equivalence. So maybe a first example is state preparation or cat state preparation. Usually in the literature, we would see some sort of definition of like a circuit C fault-tolerantly prepares the cat state. If a fault of weight T occurs, it's either detectable or it creates at most T errors on our outputs. Now, this is actually exactly the same as saying a circuit C fault-tolerantly prepares the cat state if it is fault equivalent to this idealized specification of a cat state, where in this idealized specification, the only allowed faults are kind of edge flips at the very end. Because what this means is that any fault of weight T on C must either be detectable or have a corresponding fault over here of at most the same weight. And I'm realizing that I'm doing a lot of stuff with my mouse that you guys can't even see, but I hope you get what I mean. Right, so this means that C is fault equivalent to this idealized specification if and only if it fault tolerantly prepares the cut state. And another example might be fault-tolerant syndrome measurements. Usually in the literature, we see a definition that goes along the lines of if at most T many errors occur, we create at most T data flips and or a flip of our measurement outcome. And that's actually the same as saying, look, C fault-tolerantly implements a syndrome measurement if it is fault equivalent to this idealized specification, the ZX diagram that we've drawn here. Now you have to do a little bit of work to kind of make sure that this is indeed the specification, kind of the ZX diagram that you would like to have. But this is exactly the ZX diagram that captures what we mean when we say, I would like to have a fault-tolerant syndrome measurement. And then a final example is fault-tolerant syndrome extraction. This is the idea of like, I want to actually measure all a generating set of my stabilizers for a given code. And we say a circuit fault-tolerantly implements a syndrome extraction if it is fault equivalent to kind of fault-freely measuring each individual stabilizer. Here indicated via the purple edges, we've idealized these edges as being fault-free. So each measurement should be fault-free with nothing going wrong in between.
Oh, sorry, Ben,
Yes.
I have a question.
Yeah.
So if you go back to the measurement, why the right-hand side is not purple? Like the connection between the Z spider and the red spider.
Yeah. I mean, this is kind of more of a technical thing because it's not idealized as fault-free, it's idealized as fault-tolerant. So we say we allow faults to happen on our fault-tolerant syndrome measurement. For example, like the circuits that Shaw provides, Shaw-style syndrome measurements satisfy this equation. They allow certain faults to happen. So he doesn't actually require them to be perfect. He just requires them to be good enough. And that allows him to then compose them together in such a way that they become kind of actually fault equivalent to this more general task.
One way, if you go back one slide, one way you would think about this is you could try to unmerge some spiders from for example, the red spider. But since you don't want to introduce any new fault locations, those new edges would have to be idealized. So you cannot, like the right circuit is, the right side is not directly a circuit. You cannot really implement this exactly. But if you want to create a circuit, part of the circuit would need to be idealized, except if you find the left-hand side and it's fault equivalent.
Okay, so one question we might then ask is, how do we find these circuits, right? How do we solve this problem of finding? So, I mean, a lot of like the problems in the literature basically boil down to, oh, I have this idealized specification of what I would like to have, what circuit I would like to have and how it should behave under noise. How do I find a circuit like that? And here we can use the ZX calculus, right? And this is exactly the procedure that I showed earlier for the noise-free preparation of the cat state, where we said, okay, we translate our specification into a ZX diagram, an idealized one that we can't actually, that is not expressed in terms of things I can actually do on my computer. But if I now kind of rewrite that diagram while preserving fault equivalence, then eventually I might actually get something that is expressed in terms of executable like components that I can actually run on my hardware. So one question is, do we actually have these rewrites? Because previously we've only cared about semantic equivalence, about preserving the underlying linear map. Now we have to be more restrictive. We not only have to preserve the underlying linear map, we also have to preserve fault equivalence. And this is where the idea of fault equivalent rewrites come in, because we can actually identify rewrites that do preserve semantics and fault equivalence. So for example, this well, rather simple looking rewrite. But essentially what we can do is we can come up with potential rewrites, and the way we check correctness is, well, one way to do it is to literally brute force it, right? Check all fault combinations on the left and check them against all fault combinations on the right, and vice versa. The nice thing is that these circuits are relatively small, and once we've checked their correctness, we can actually then use them in any context. So we can kind of go through these rewrites and check that they are actually in fact fault equivalent. And we can come up with rewrites that actually introduce new detecting regions, so new detecting sets, in case you know what the detecting regions are, but these kind of give us new syndrome outcomes. And we can actually come up with rewrites that are actually entire families of rewrites. And now with all of these tools put together, we can actually give an answer to this question: how do I find fault-tolerant gadgets? So let's start with something simple. Let's start with the fault-tolerant cut state preparation. Let's start with wait for. So now I want to find a circuit that is fault equivalent to this idealized specification. The way I'm going to do this is I'll first translate it into a ZX diagram, and then using our rewrites, we can start manipulating that circuit until eventually we get something that once again looks like a quantum circuit. And this circuit that we got here, that's actually this is the circuit that we originally had, but now it's surrounded by a flag measurement that makes sure that kind of catches the faults that would have otherwise propagated badly. There are you have to take a little bit of care when stepping from ZX land to circuit land and vice versa, because we kind of care about slightly different notions of, well, slightly different noise models, right? We care about circuit level noise over here, while we care about edge flip noise over here. So there is a little bit of nuance here that I'm glossing over, but this is indeed something we can take care of, and there are some more details in our paper. So the way people usually one way to construct these kind of fault-tolerant circuits is by starting with a non-fault-tolerant one, checking for all possible error combinations that propagate badly, and constructing the corresponding flags. We don't have to do this. This flag kind of just fell out of our derivation. This thing is correct by construction. We don't have to check its correctness because we know it's fault equivalent to this, which is fault equivalent to that, which eventually is fault equivalent to our idealized specification. And one thing that this allows us to do is to actually, for example, prepare cat states for arbitrary weight. So we can actually prepare arbitrary weight cat states. We can prepare 2n-legged cat state using our rewrites from 2 n-legged cat states, then using the transversal and using a sequence of transversals at measurements. Just to give another example of where we can use fault tolerance by construction, a fault-tolerant syndrome extraction is another example. So this was exactly what we were talking about earlier, the question of find me a circuit that is fault equivalent to this particular specification. And one solution to this problem is given to us by Shaw, right? And we can use our rewrites to verify the correctness of Shaw-style syndrome extraction. So we take our specification, and then using our fault equivalent rewrites, we manipulate the specification until eventually we get a quantum circuit. And this is exactly the circuit that Shaw proposed. And the way we usually prove correctness of this circuit is by appealing to its transversal nature. In our proof, that doesn't actually come up. We have shown correctness because we were able to construct it using fault equivalent rewrites. And one thing that this allows us to do is we don't have to stop here. We can actually take what Shaw proposed and continue rewriting it. As long as we preserve fault equivalence, we can start optimizing circuits in the literature. So for example, this only connectivity rewrites rule, where we can move spiders around, actually allows us to take these two measurements here and bend them around. All of a sudden, we get a new circuit that is still equivalent to our specification, that still fault-tolerantly measures a syndrome. However, it only uses 2 auxiliary qubits and 2 measurements instead of 4 auxiliary qubits and 4 measurements. And as a last example, we can actually do the same with Steen-style syndrome extraction. Steen one-shots the problem of syndrome extraction, so he solves this problem of doing all the measurements fault-freely in one go. And we can once again use our rewrites to verify the correctness of Steen-style syndrome extraction. But once we've done that, we once again don't have to stop there. We can actually now take Steen's solution and start rewriting it further, kind of just go a little bit further, optimize a little bit, try to get those resources down. And eventually we get a new circuit that uses fewer qubits, fewer measurements, and fewer CNOTs. And if we actually run that circuit in simulation and compare it to Steen's original proposal, we can see that it does indeed outperform the original. So this is kind of the basic idea of fault tolerance by construction, right? The basic pitch is we care about not just semantic equivalence, not just circuits implementing the same linear map. We actually care about fault equivalence. We care about our circuits behaving in the same way. And if we take that realization and kind of run with it, what we can do is we can come up with new gadgets. We can verify existing ones. We can come up with new ones, and we can optimize existing ones simply by taking our fault equivalence rewrites and using them to do new things. So this is kind of the cut here. This is the notion of fault equivalence. And if there are any questions, this might be a decent point. Otherwise, I'll immediately jump into kind of the second part, which is completeness for fault equivalence.
I do have a quick question. So you've mentioned two applications of this. One is generating new fault-tolerant circuits. The other one is verifying existing fault-tolerant circuits. I think that second, I mean, the first one is of course super interesting, but I think the second one is also very, very interesting because usually how fault tolerance is checked is by brute force or by appealing to construction and then checking it in a painstaking way. So my question is, how far do you think this is to being able to be used as an like automated tool that proves that it is fault tolerant?
Yeah, very good. Yeah. So checking fault equivalence in general is NP hard and can be shown to be NP hard. And indeed, this is like very closely related to the second part of this paper, the completeness question, where we also actually eventually come up with a procedure for automatically checking fault equivalencies. So a very general automated procedure is indeed still has to iterate basically all error combinations is the high level observation. Where it becomes easier is if you can find a neat sequence of rewrites. It's not always easy to find that sequence of rewrites. So if you give me a random diagram and ask, is this fault equivalent to another random diagram? I might have a difficult time doing that. But indeed, there is a procedure for doing that, which I will talk about now.
Awesome.
So, yeah. And that's indeed the question of, well, it's closely related to the question of completeness. So far, we've been using the soundness of our calculus, right? So this idea of like, oh, if I can rewrite one diagram into another, into another, into another, then eventually I'm guaranteed that the first diagram is fault equivalent to the last one. So basically what this is saying is I cannot derive wrong fault equivalences. Our rewrites are sound. But a very natural question you might now ask is, look, I have two diagrams that I know to be fault equivalent. Does there exist a sequence of rewrites that gets me from one to the other? And that's the question of completeness. So that's kind of a question that you might very obviously ask about a rewrite system. And this is what we've been tackling in the second paper, which eventually also does lead to a procedure for automatically checking this, but it is NP hard. So, you know, this is computationally difficult still. So the set of rewrites that we are proposing to be sound and complete is this set of rewrites. I think the exact technical details are not important, but the basic idea is we have the rewrites that we know to be complete for fault-free stuff. We kind of don't really care about global phases, so we have certain rules to get rid of them. And then we have ways of manipulating our noise model. So there are different ways of proving completeness, but I think one of the most common ones, especially for kind of new completeness results, is via a unique normal form. So what we say is if we can identify a unique representative per equivalence class, then we can rewrite different elements in that equivalence class by going via the representative. So I can rewrite some element 1 in my equivalence class into the representative and then do the rewrite in the other direction into some other element of my equivalence class. So kind of these unique normal forms are one way to prove completeness of a rewrite system, and this is exactly what we are going to do here. For that, a little bit of preliminaries. one thing that I'm very fond of these days, and I think quite a few people are at also PsyQuantum and in Berlin and stuff, is this idea of Pauli webs. Pauli webs are a decoration of ZX diagrams. They're a way to highlight the edges of a ZX diagram that satisfies very specific rules. And they are quite useful to reason about diagrams. So mathematically speaking, we can actually model a Pauli web as an element in the Pauli group to the number of edges. So type-wise, it's actually the same as a fault, right? Pauli webs and faults have the same type, but these are kind of very specific faults that have to satisfy very specific conditions. And in particular, these are local conditions that they kind of interact well with the spiders. In particular, what we say, the way this picture on the right here and the Pauli corresponds is that we say, look, if an edge has a Z flip, we highlight it in green. If an edge has an X flip, we highlight it in red. And if an edge has a Y flip, we highlight it in red and green. And now we say an element in the Pauli group to the number of edges is a valid Pauli web if for all spiders with a phase of 0 or pi, it highlights an even number of edges in the color of the spider and all or none of its edges in the opposite color. And then for spiders with a phase of minus pi over 2 and pi over 2, it has to either highlight an even number of edges in its own color and none in the opposite color, or an odd number of edges in its own color and all in the opposite color. And essentially what these conditions require is that our spiders represent Clifford diagrams, right? So they are stabilized by Paulis. And essentially what we're saying is the local highlighting around a spider should correspond to a stabilizer of that particular spider. And Pauli webs are really quite nice because they help us to track things such as stabilizers and detectors. So one kind of class of Pauli webs that we care about is the so-called stabilizing Pauli webs. A Pauli web is a stabilizing Pauli web if it highlights no input edges of the diagram. And essentially, what this means is that via kind of these local stabilizers of our spiders, we're guaranteed that if we have a stabilizing Pauli web that kind of highlights the boundary edges as Zi, Zz, then the overall diagram actually stabilizes the Pauli string Zi, Zz. So every stabilizing Pauli web corresponds to a stabilizer, and also vice versa. For every stabilizer of our diagram, there exists at least one corresponding stabilizing Pauli web. And then another class of Pauli webs that we care about quite a lot are so-called detecting regions. Detecting regions are Pauli webs that do not highlight any boundary edges. So they only highlight internal edges. And it turns out that detecting regions are actually in direct correspondence with detecting sets. So for every detecting set, there exists a corresponding detecting region and vice versa. And what we have with detecting regions is that if we have a fault that anti-commutes with a Pauli web, and here we make use of the fact that both of these are just elements in the Pauli group to the number of edges. So if these two Paulis, if they anti-commute, what this means is that that particular fault is detectable by this detecting region. What that means is that this particular fault will flip odd many measurements in this particular detecting set. So one thing we can observe is that a fault is detectable if and only if it anti-commutes with some detecting region. And another thing that we kind of make use of in our completeness proof is this idea of fault gadgets. Fault gadgets are a way to diagrammatically track the effect of faults on diagrams. So we have these so-called Pauli boxes, which are just very specific ZX diagrams that we can just define. And the idea is if I have, for example, let's say I have 4 qubits and I have a fault of weight 3 of type IZXY. Right, so I have a noise model that is not an edge flip noise model because I have atomic faults that affect more than one edge. Then what I can do is I can instead provide a different diagram where I add a so-called fault gadget. And what this means is that all of a sudden there exists a new edge on this new modified diagram where a single fault on that one edge has the same effect as this entangled fault. So if I now have a single Z flip on this particular edge, that actually has the same effect, Z, X, Y, as my original fault. So instead of having to track kind of these, what this means is that if we have a non-edge flip noise model, we can always modify our diagram by adding these fault gadgets, such that we can find a new diagram under edge flip noise that is fault equivalent to our original. So these fault gadgets are a way to kind of make life a lot easier for diagrammatically tracking the effect of faults on diagrams. Okay, so to do this completeness proof, we had to do a little bit of fun new theory, which I think is kind of quite interesting also beyond the scope of this paper. So I will go into a little bit of detail there, and then I might skip a little bit on the details on the exact construction of a completeness proof. But I think these are kind of very interesting ways of identifying faults in space-time that might be quite useful also beyond the completeness proof. So let's define a specific class of faults. We call them inconsequential faults. You might also know them as trivial faults or something. There are different names out there at the moment in the literature. And these are simply faults that if they happen, they don't actually change my diagram, right? So if, for example, a fault happens to correspond to a stabilizer of my diagram, it doesn't do anything. I don't really care about it. It's inconsequential. And examples of inconsequential faults are, well, the trivial fault is inconsequential. Kind of stabilizers of spiders are inconsequential, but there might also just be faults that are kind of spread out in space and time that happen to propagate in such a way that they cancel each other out. And based on this, we can actually define a new equivalence relationship on our faults. We say two faults are space-time equivalent if there exists an inconsequential fault that multiplied together with the one fault gives us the other fault. And basically, in error correction, we mostly care about like equivalence classes, space-time equivalence classes of faults, right? So if I have a C0, whether I have a single X flip on the control before the C0 or two X flips after the C0, I don't really care. There's actually no way of me telling in my decoding procedure which of the two happened. All I want to do is identify the equivalence class of faults. And there are some nice things, and this is kind of what I was alluding to earlier, that I think is quite cool. We can actually fully identify the space-time equivalence class of a fault in terms of its interaction with the Pauli webs. So in particular, a fault is inconsequential if and only if it commutes with all the Pauli webs. Well, it has to commute with the detecting regions because we said it was otherwise it would be detectable. It would make the diagram go to zero. And it also has to commute with all the stabilizing Pauli webs, because if it anti-commutes with a stabilizing Pauli web, essentially what it does is if our diagram previously was in the +1 eigenspace of that stabilizer, a fault anti-commuting with that stabilizing Pauli web will create the faulty diagram will now be in the -1 eigenspace of that stabilizer. So if an inconsequential fault doesn't actually change anything about the diagram, it must commute with all Pauli webs. And then we can say that two faults are space-time equivalent if and only if they anti-commute with exactly the same Pauli webs. So we can fully identify faults via their commutation relationship with Pauli webs. The way we can see that is if they are space-time equivalent, there exists some inconsequential fault that makes them the same, but S must commute with all Pauli webs. So F1 and F2 must anti-commute with the same Pauli webs. And similarly, if F1 and F2 anti-commute with the same Pauli webs, then the product of the two Paulis must commute with all Pauli webs. And we can use this, we can kind of use this in our completeness proof, because now what we can do is we can kind of identify these so-called flip operators, which are, well, you can think about them as destabilizers, but instead of destabilizers for our stabilizers at the end of the circuits, they're actually destabilizers for our Pauli webs. So for a given basis of our Pauli webs, we identify for each basis element a specific fault that anti-commutes with exactly that basis element and commutes with all the other basis elements. And this gives us a way to uniquely represent all the equivalence classes, because if a fault is fully identified by the Pauli webs it anti-commutes with, we can actually express all the faults in terms of flip operators. So one example of this might be that we have some basis of our Pauli webs, and we identify these specific flip operators, and then we can actually express all the faults solely in terms of the flip operators. And what we now do is that for all the flip operators of the stabilizing Pauli webs, we identify faults on the boundary, and we can show that this is always possible. So what this now means is that all the undetectable faults will only affect things on the boundary, while the detectable faults will actually still consist of flip operators internal to the diagram, because the detectable faults have to still anti-commute with some of the detecting regions. I mean, the overall idea of what we were doing here in our completeness proof is really the idea of like we try to get the faults out of the way, right? So we kind of fault equivalence is this question of do the diagrams implement the same linear map, and do faults have the same effect on our diagram? And what we are now going to do with all this theory is try to separate the semantic part of the diagram, the linear map, from the effect of the faults. And what we've now done with these flip operators is we basically have only actions on the boundary, except for some very specific actions that anti-commute with certain detecting regions. And then using some additional rewrites, we can actually kind of get those flip operators inside the detecting region to pop out in some sense as spiders. Again, I think the technical details are not particularly essential here, but the high-level idea is that what we now have is for every detecting region, or every basis element of our detecting regions, we have a separate spider. And for every fault, we have a fault gadget. And now every fault is connected to the corresponding detecting region spider, if and only if that particular fault anti-commutes with that detecting region. So what we have here is a diagrammatic representation of the detector error model. We have our detectors on the one side, these free-floating green spiders, and we have the fault gadgets, the errors, on the other side that are connected to exactly those detectors that they violate. And then once we've kind of pushed out all these faults to the boundary, we still have to take care of kind of all these different faults on the boundary, and we have to compare. So if we have two diagrams and we've each pushed out the respective faults to the boundary, we then have to compare if kind of these faults on the boundary of the two diagrams have the same effect. And this is in fact kind of where the exponential blow-up comes in. The high-level idea of what we do is we kind of get rid of the detectable faults and replace them with undetectable ones. And then we really have to iterate all equivalence classes of faults and check their respective weight to make sure that the two diagrams are fault equivalent. So that's kind of the high-level idea. I think the main takeaway of the second paper is A, we have a complete set of rewrites, which is quite nice. B, I do think that there is some math here that is just useful, kind of thinking about space-time equivalence classes of faults in terms of Pauli webs and kind of connecting all of that in, I think, quite a nice way. And then the final thing is that we actually do have a general procedure for checking fault equivalence. Now, this is NP hard and kind of this is a lot of work, but this is something that we can actually implement. And Max will now present some of the work that we've been doing in that regard on kind of implementing some of these first things. I think there's still work in progress. We're still kind of optimizing the speed on some of these aspects, but at least it showcases kind of how this would look like. So I'll just immediately hand it over.
Yeah, thanks, Ben. I'll try to share my screen if Firefox lets me. So yeah, the example that we're trying to work through is we're trying to check the fault tolerance of a particular state construction. In this case, it would be the zero logical state for the Steen code, and we're trying to verify that the on the right hand side here, the circuit that go to 2016 that he proposed is actually fault tolerant, in the sense that it is fault equivalent to this idealized description of that state. Now, the left-hand side can be obtained by converting the right-hand side to a ZX diagram, idealizing everything but the output edges, and then using these idealized versions of the regular ZX calculus rules to squash everything down. You don't have to apply these rules, but it makes for a nicer description of the state, a smaller one. So the first thing that we need to do in the library is to, if you're familiar with PhySX, which is the general library for ZX calculus, you need to construct your diagrams. So we'll construct the diagrams one by one. Here's the left-hand side. We'll also construct one for the right-hand side. And then the first step to finding the equivalence classes of our faults, which we have not yet specified, but we need to do that anyway, is to compute the Pauli webs of these circuits, or these ZX diagrams in this case. And the library exposes a little function here, compute Pauli webs, and returns separately the stabilizers and the regions of those Pauli, the stabilizing Pauli webs and the detecting Pauli webs, which we call detecting regions. And then if you run this, you actually get the feedback that for the ZX diagram representing the state, it found 7 stabilizers, which is a good thing because that matches up exactly with the number of qubits. And we also found 7 stabilizers for the circuit, but we additionally found a detecting region. Now, this detecting region, this extra detecting region that we do not have on the left-hand side, is sort of characteristic for us performing this verification step of having this in silico qubit measuring, performing a few C-nodes, and then at the end measuring. Goto, in his paper, post-selects on the 0 outcome, I believe it is, which is exactly what we do here in the select diagram. We post-select on the 0 outcome. So this node 37 would be the measurement node. And this forms a detecting region. So that means that if a fault flips our detecting region or violates our detecting region, then this measurement would flip, and the actual probability of obtaining this exact diagram with measurement 0 goes to 0, which detects the fault. Next, what we need to do is specify noise models. There are some helpers in this library to help you do that, especially for weighted noise. And what we need to feed in is the ZX diagram that we use, individual weights for the different types of faults, so X, Y, and Z. In this case, we chose a CSS noise model or CSS-like noise model. You will express this in this library as having a weight 1 fault for X and for Z, and using a weight 2 fault for Y. And then we need to specify which edges are idealized. So in our description above here, every edge that is internal to the diagram for the state is idealized. And the way I express that is just by taking each edge that is incident to a red spider. On the right-hand side, we have no idealized edges. So what we do is, on the left-hand side, we specify this via a regular Python array comprehension. And for the second noise model, we specify that no edges should be idealized. You could also omit this, but to be explicit, I left it in. And then we can simply call is-fault equivalence to ask the library whether those two noise models are equivalent. And it will return true, verifying that this implementation of Goto is actually fault tolerant, in the sense that it is fault equivalent to this idealized specification. The library also can give you more information if you type quiet false. Then it will actually show you how far it got, which steps it had to perform, and how fast it performs them. And you can see here that we found 21 atomic faults for the first diagram, which is the state diagram, which makes sense because we had 7 output qubits, so 7 output edges, 7 boundary edges. Those were the only ones that had faults on them. And we had 3 types of faults, the X, Y, and Z, so 3 times 7, 21. For the second diagram, we obtained a lot more atomic faults. And now what this algorithm does is try to find a counterexample to fault equivalence. And it's trying to be smart about it and trying to take shortcuts. But in the end, you can see it takes up to exploring faults up to weight 6 until it runs out of items to check, until it can verify I have found no counterexample, thus it must be true. And then it reports true at the end. Of course, these are not that many atomic faults. If you have large diagrams and a lot of faults, the intermediate steps can blow up very quickly and leave you with basically leave you stuck. It might also fill up your RAM. That depends on the case. But right now, depending on which iteration you're in, you might get 2 million iterations per second or higher. That also depends on your CPU, of course. But yeah, that's kind of the library. Ben had a link where you can fetch it. It's currently only on GitHub, but it's planned to be on PyPy. And whenever there's a Rust implementation, also on crates.io. And the library's name is Parity under the GitHub org Parity. Yeah, that's it.
Great. Thank you very much. All right. Are there any questions from the audience? Yeah, feel free to unmute yourself. Yeah.
Thank you so much, Ben, for the talk. I wonder, earlier you were talking about one detecting region correspond to a spider, and this spider is corresponding or is connected to a fault gadget. And you also talk about equivalent faults. So like if you have two diagrams and there are faults on them, that they turn out to be equivalent, like are you just representing this as a one fault gadget connected to the detecting region?
Wait, Max, if I can share again, if you stop sharing, then I can share again. I mean, essentially,
Yes.
like this is something that you have to take care of in the completeness result by actually iterating, by adding a rule for kind of getting rid of duplicate faults. So that's kind of, I think, so if you have duplicate faults, you can just rewrite them. You can remove one of them using one of the rewrite rules.
Oh, sorry, I do not mean like two same fault appear like two equivalent fault appearing in the same diagram. I
Yeah.
meant in two different diagrams, and then you have each has a fault, and they turn out to be equivalent, has like this space-time equivalence that you talked about. How do you identify them in your this gadget notation?
Right. Yeah, so we show that you can rewrite fault gadgets into space-time equivalent fault gadget one. So that's part of the proof is that if you have a fault gadget using our rule, you can actually rewrite it into a space-time equivalent fault gadget just using kind of the proposed rule set.
Cool. And also, I wonder when you're working with this Sting code example, have you observed that because you are working with a CSS code and you essentially have like very structured circuit than just any linear map, are you able to take advantage of the CSS code specification to eliminate the search space or to speed things up a bit compared to just brute force everything?
That's in theory possible at the moment. That's not something we're explicitly doing.
Okay, thanks.
Yeah, and I mean, some things to mention also about the implementation is kind of this idea of like once we formalize the idea of fault equivalence further, there are ideas on how to kind of further improve on this, either by combining it with the rewriting system or also kind of doing fault boundedness, kind of approximate fault equivalence. So saying that one circuit is no worse than another circuit, which might actually allow us eventually down the line to kind of simplify some of these verification processes.
Thanks.
Two questions real quick. One would be, you said earlier, like, is this only for Clifford circuits it supports, or is there some way to incorporate non-Cliffordness here?
At the moment, it's only Clifford. I mean, thinking about more generally, thinking about like non-Clifford, like Pauli faults and faults in non-Clifford circuits is very difficult. I mean, it is something we've started considering. I think it would be really cool to also have the fault equivalent rewrites in a non-Clifford setting, for example. At the moment, we only have fault equivalent rewrites in Clifford settings. it creates a whole bunch of like questions and problems and challenges that I think would be really cool to tackle. I'm slightly terrified of them, but it is indeed something we have started thinking about. But I'm not expecting it to work out quite as nicely. So there's always this trade-off of like what exactly you look at. Yeah.
And then second question, I'm not sure exactly how to put it in the language you presented, but the idea is like, you have one circuit, maybe the idealized circuit, and then you have a circuit that you've come up with. Maybe there's some other external constraints due to hardware or something, and you want to check that they're equivalent, but you're okay if you lose some distance in that process. Like maybe something was distance 5 protected, and now you lose one you go to because you really need to hit your constraints. Is there some way to capture that kind of tolerance in the fault equivalence in this methodology with like the weight definition of that?
Yeah. So there were different things where we've been thinking about like how to kind of make fault equivalence less strict, right? So maybe you have a two-fold equivalence. Every one fold only propagates to at most 2 or like twice its weight. I think those would be kind of interesting things to look at. We haven't really fully done that yet. In part, that's not transitive, right? If I have, or well, at least it multiplies up. So there are kind of some nuances that you have to take into account there that make it a little bit more difficult. One thing that we've been definitely thinking about is what we call T-fault equivalence. This is actually transitive, where we say we only care about faults up to some weight T, and then everything above is irrelevant, because if we live in some sort of code that only has some distance, we don't have to protect against everything. We only have to protect against up to some weight. So that's definitely a less strict version of fault equivalence that is quite useful. Other versions are not something we've fully kind of thought through quite yet. Yeah. Would be interesting though, yeah.
Thanks. And also thanks for the code. It's exciting to see the code already here. That's really cool.
Yeah, this notion of limiting the fault equivalence is already in the library. So you can limit your search such that you kind of give up finding a counterexample at some point. And I have one optimization in mind where it might actually speed up the intermediate process of you finding the counterexamples for weights where you do care about it. Because you could skip, for example, inserting items into a queue where you know you won't handle them at any point because they're too high weight. And like little nitty-gritty, almost algorithmic details to speed things up. But yeah, right now it's Python only, and you might get another big boost from rewriting Rust.
I have a question about the post selection. So suppose that we're thinking about a more general scenario of the CSS state preparation, and then you post select based upon the expected syndrome outcome, and then you then measure out the data qubits to see what exactly are you preparing, and how is this success rate of getting what you want related to this T-fault equivalence notion that you just mentioned?
Okay, so one high level thing here is this question of like what is actually the noise that we are considering? And I think this is an interesting question, right? So what we are considering here is this adversarial notion of noise. We just say, look, there is some weight, and we kind of ask if a fault of up to weight something happens, what's the worst that could happen? And I mean, this is very similar to also what Gottesman does in his framework. So like, for example, Gottesman extended rectangles can also be expressed in terms of kind of this adversarial kind of fault equivalence. One question that we are thinking about at the moment is how do you generalize fault equivalence to other noise models, to stochastic noise, where you kind of assign your faults a probability instead of like a weight, and you ask, what does that actually mean? How do I think about circuits under stochastic noise rather than adversarial noise? And I think these questions of like, for example, success rate, but also logical error rate, all these, like the moment you ask about that, that's a stochastic question that is like not just dependent on the distance of the circuit. Essentially, what we're asking at the moment is what's the distance of my circuit? So like our fault equivalent rewrites are actually also like we originally proposed the idea of distance preserving rewrites. So the set of all rewrites that preserve the distance of your circuit, which happens to be exactly the same as the fault equivalent rewrites. But what you are now asking about is more is a slightly different kind of question of like what is actually the behavior under stochastic noise, under like what's the probability of an error, which is a separate question that we are starting to think about also in terms of fault equivalences and stuff. But obviously, once again, it's one of those cases where things get a lot messier the moment you step out of the simple, nice Clifford adversarial setting. Yeah.
And just now, the rules that you presented, they are under the adversarial noise model. So at the beginning of the talk, you give us a weighted edge diagram, but your rewrite rules is not about the weighted edge.
No, that's an adversarial noise model that kind of falls within the categories of adversarial. So it is under the weighted edge noise model. The stochastic noise models are the ones where some of the rewrite rules that we have at the moment would fall apart. Yeah, where preserving equivalence under stochastic noise is much more difficult than preserving equivalence under adversarial noise. And there I'm expecting really this fault boundedness to play a much bigger role where you kind of say, look, it's no worse than this circuit. So if this circuit has a logical error rate of X, then I'm guaranteed that my original circuit has an error rate of at most X. So kind of only kind of requiring faults in one direction to not be worse than in the other direction, which yeah, it will be a slightly different way of working, but it'll interact closely with the adversarial things.
But I
One
wouldn't. Oh, sorry, you go first.
Sorry. One thing to note here is that you can reach the form where everything's pushed out. It's not necessarily normalized yet, but where everything is pushed out, you can reach with any noise type because you're not interacting with the like you're required to be Pauli faults, but you're not interacting with the actual values you assign it yet. So in the noise model, we assigned it integers for weight, and we only interact with those integers once we start to normalize this like separate section, separate to the idealized description of a diagram. And this is also reflected in the library. You can perform every step up to that normalization without kind of giving any way to interact with these values. But once you want to start, for example, checking for equivalence, you're restricted to weighted noise.
Mm.
So those are kind of the two, and you need a distinctly different set to normalize. So this distinctly different set requires you to have a like well-defined interaction in some sense between your weight values or probabilities or whatever you use. And we're still working on like kind of ironing out the details of which exact conditions do your values need to fulfill for you to be able to perform this normalization, or what kind of normalization can you perform under different conditions. That's still something to find out.
And whenever you talk about normalization, you're talking about this pushing out process, about pushing the errors to the boundary.
And no, I'm first. I see pushing out as a separate step. I push everything out to the boundary, and once everything's at the boundary, then I try to compare um, to noise models. So if you remember the pipeline of those three diagrams that Ben showed, in the first step we had the like noisy diagram. In the second step we had the separation, and you can reach the second step with any value, and any values attached to your faults. But the final step, so far we've only shown to be nicely reachable for weighted noise.
Thank you.
Yeah, exactly this slide.
Mm. Oh, can I ask one more question if no one is asking? So, like I noticed that a lot of the times, if you're only transforming the diagram in the direction that you do not reduce the distance, it's much easier to reason than this bidirectional fault equivalence. What would happen if you only allow the one directional fault equivalence? Do you have more rules in your rule set that we can use?
Yes.
Uh,
Yes, you'll have to
yes.
add one. You have to add one more rule essentially to get completeness for that. So maybe maybe here's a high-level observation about the rules that we also propose in this completeness paper. I think this is an interesting point to make. Like the completeness rules that were proposed for the Clifford ZX calculus in the noise-free case are actually also the rules that we work with a lot on a daily basis, right? These are very useful rules of manipulating the diagrams. I think some of the rules in this way we get to our normal form by just using the fault gadgets and stuff is not very much related to how we actually think about it in practice, like how we use it in a day-to-day. I think in a day-to-day we use these derived rules where we've once shown that this is a useful rule, and then we just use that instead of these kind of atomic rules or axiomatic rules that we propose here in this paper. So it is enough to add one more rule to get the fault boundedness rather than fault equivalence. But I'm expecting that to give you a lot more derived rules that you can work with down the line. Yeah, it has advantages, has disadvantages to work in this fault bounded way. But like, yeah, indeed, that can also be thought about in terms of like this completeness setting.
And for software, is it easier to check this fault boundedness as opposed to fault equivalence?
It will be easier. It is not yet implemented, but you need to store less data. You have less memory overhead. Because right now I'm generating all new undetectable faults that could be counterexamples for both diagrams separately, and then checking for consistency for both for each weight level iteratively. And you could, for example, omit one of those data structures, and just from a like memory pressure perspective, the less you have to insert the data structures, the faster your program will get. So yes, it will speed up things if you only care about one direction.
Thank you.
Right. Yeah, thank you very much. I think we are over time. So let's thank our speakers again. It's a great talk, and we'll post the recording on the website. Yeah, thank you again for coming, and thanks everyone for joining the seminar today. We'll see you in next week. All right.
Thank you very much.
Thank you, everyone. Bye.
Thank you. Bye-bye.
Bye.